Hi, my name is Dr. Ji Sun, and I'm a professor of psychology and cognitive science at Cal State LA. I'm a co-founder of CourseKata.org, and I'm here to talk to you about how we could use data science to reignite students' interest in math. Let's dive into using data science to reignite student engagement in high school mathematics. Me and my co-author, Jim Stigler from UCLA, we have been doing data science and statistics education research for a long time. And one of the things that really interests us is how do students learn things that are hard to learn? We come at this from the point of view of being learning scientists, cognitive psychologists, who are really interested in making sure that what we're doing in education is driven by research and data. Now, we don't want to just write papers that nobody else reads. We actually want to make a difference in real classrooms with real students and teachers. And so we have developed what we call the Better Book Model. It's a mechanism for making course materials better based on data through a collaboration of researchers, instructors, as well as designers and developers. And so I want to take time to just acknowledge all the different team members who are just so valuable to our project, who are not here today. We're representing them. We hope to do them proud. I want to start with the state of high school algebra, which might seem like a strange place to start for a statistics and data science project, but this is the kind of thing that keeps us up at night. Almost 34% of students in California take Algebra 1 at least once, and this is not an uncommon statistic across the different states. 44% never complete 2 semesters of Algebra 2, and that's just talking about completion and throughput, let alone what they actually learn about algebra. But here's the thing, this is a surefire way to kill students' curiosity. And that's a really unfortunate thing because y equals mx plus b is one of the most important math concepts to learn. And we would love it if students could really see, wow, this concept, so important, so applicable to so many things in the world. But that's not what they think when they learn this concept. In fact, when we think about all the different things in algebra and K-12 mathematics, so many things are important. All these little bits, they're really, really important. But students learn every single one of these things, and it takes them an incredibly long time and a lot of effort to learn each of these things. At the same time, they don't see the connections between them. And because of that, they can't transfer this learning to new contexts. They don't go out there and think, wow, all these concepts super applicable to the world and the questions I have. That's a tragedy. And that's the problem that we're very interested in working on. We come at this from a learning science perspective. And so we looked to the research and we saw that what experts have is coherence and connections between their concepts. They don't think of a domain as hundreds and hundreds of tiny little bits. They think of it as a few concepts that intricately relate to each other in such a way where if they forget one of them, they could just reinvent it using the other ones that they know. These connections, they are the basis of their ability to transfer their learning to new contexts. So we as psychologists thought, there's a theory here. It's a pedagogical theory that we call the practicing connections hypothesis. So if you apply the idea of practicing connections, that students should actually practice just making connections rather than learning all these tiny, tiny bits, then we would predict that their learning would be more transferable, that they would be motivated to learn more complex concepts to fill out their web, and it would foster interest in more STEM courses, majors, and even careers, because it would connect what they know to the world and the things that they're actually curious about. And so we started this project by starting in statistics and data science. That's a course and a content area that a lot of people teach, a lot of people try to learn, and it's really hard to learn. So it's that sweet spot of what we're interested in. And we developed over 6 textbooks now, focusing on how to teach statistics and data science using the practicing connections theory. Our statistics textbooks are now being used at over 60 colleges and over 60 high schools. And so we're growing every year. We hope you'll check out coursekata.org if you're interested in joining us. And I want to tell you a little bit about how we implemented the practicing connections hypothesis in our course kata materials. The key features are that we interconnect everything in the course to the concept of statistical modeling. This idea that data equals model plus error, which means almost nothing to students at the beginning. But it's a really important concept in this modern world, and it's deeply related to algebra. So this is the basis upon which we've built our course. Our course takes a computational approach where we have a gentle introduction to R. We use simulation, bootstrapping, randomization, and we use Jupyter notebooks, which are an authentic tool used by many data scientists. And finally, as psychologists, we know how important the concept of randomness is, but how difficult it is for humans to understand. And so we try to teach students randomness as not a set of principles, but as a data generating process, that randomness itself can generate patterns of data. And we want to say a word about algebra. Algebra is highly relevant. But mastery of algebra is not assumed because we know the world that we currently live in. Even a lot of our students who pass these courses, they come into our courses not quite having a mastery of it. But I want you to take a look. This data equals model plus error. And we use the notation of the general linear model. And I want to point out that this is just professional algebra. This is the algebra that's published in journal articles in economics, sociology, and beyond. And we want to say, hey, that's just high school y equals mx plus b, but kind of fancified with small subscripts. Why not teach students the way that algebra is going to get used in the future? Just teach it to them in high school. And so our course is embodied in two sets of materials, an interactive textbook that teachers often use to assign for homework, and a full set of Jupyter notebooks, which teachers often do in class and use them as the basis of projects. And our Jupyter notebooks are where teachers have the freedom to bring in lots of interesting data cases that their students might be interested in. What predicts how much income a YouTuber makes? Can we use animal behavior to predict the severity of hurricanes? And how does the NFL treat domestic violence? And so these are the kinds of questions and data that students could dig into. And each of these Jupyter notebooks are organized around the practice of doing statistics in the world. Students start by exploring variation, then they model that variation using algebraic functions, and then they evaluate those models. Now, I want to give you an example of how we build that up in our curriculum. How do we get from exploring just ideas in the world all the way up through y equals mx plus b? And so here's an example of how we do that. For example, students will look at, hey, do happier countries live longer? This is an actual hypothesis that our students come up with once they look at this data set. And they often think, yeah, maybe countries that are happier live longer and countries that are less happy don't have as long of a life expectancy. And we get students to translate the words that they're saying, their regular hypothesis, into what we call a word equation. Life expectancy equals happiness plus other stuff. This isn't an equation yet, but it's a proto function. It's saying life expectancy is a function of happiness, but happiness is not going to be the only thing. There's going to be other stuff. We also mirror that idea in our R coding. The syntax of the R code is going to be life expectancy tilde happiness. In algebraic terms, it's going to be y tilde x. And we use that syntax because that enables students to make graphs, such as the scatter plot, where you could see, countries that tend to be happier tend to also have a longer average life expectancy. But you could also see happiness isn't everything. There's some other stuff in this picture. And from there, students could start to fit lines and come up with their own model of this variation. And they model that variation using a regular old linear equation, right? But now the focus really is on figuring out what's the best model for this data rather than solving for happiness or solving for life expectancy. Instead, they're trying to describe the relationship between happiness and life expectancy. And that's really the joy of algebra. Not only that, but we also teach students to add on the plus error term because mostly in the world, things are not perfectly defined by algebraic functions. There's always other stuff. And so our whole idea is that students go from hypotheses they actually have about the world, they translate into word equations, then they then write R code that could help them generate visualizations as well as linear functions. And then they write it down and communicate it with other people using professional algebra. And we want students to go through this and build up a meaning of what these functions mean, that they're not just things that we told them are true, they're things that students themselves discover is their expression of their idea. And this kind of flow allows students who might have thought that mathematics is just kind of not their thing, or they don't find it intrinsically interesting. We're finding that this process re-engages those students with mathematics. They're learning about functions in a way that's more transferable and applicable. They're motivated to learn more complex functions. For example, sometimes students look at other kinds of hypotheses and they fit a linear model, but they feel unhappy with the linear model. And they're like, I want to learn more math to help me model this kind of data. And it fosters future interest, curiosity, and agency in math, coding, data, other kinds of STEM-related topics. And those are the kinds of things that we love hearing from our teachers, that they say their student went off and Googled more stuff because they wanted to learn. And so we don't want you to just take our word for it. It'd be best if you hear it directly from our students. So here's just a few students when they were asked about their data science course, data science and statistics course.
I never had a good relationship with math. It was just something I really kind of try to avoid going on forth in my high school career. I really enjoyed that it's more than just numbers and formulas. It kind of has a story, like each data frame kind of brings more than just numbers when you kind of study. And it's very fun when you kind of get to learn about things that you've never really considered before, and you kind of develop an open mind towards the world, and that there's so many possibilities.
What I enjoy about data science is like being able to have different data frames to like analyze, and it's not always the same one. Like it could be about like just about like the planet, like we've seen like about bugs and birds, like how what affects that, or we've also seen like about like more, I guess, political things like presidents and elections and those stuff. So it's just like the range on what data frames we get to like analyze and use is pretty cool.
I like this because, you know, you could apply this to so many other things in the world. So, you know, like with math and like geometry and algebra and all that, you know, it's like formulas, you know, you're trying to build a building, you probably help with that stuff. But with data science, it could apply to like way, like a broader spectrum of things. So like, you know, you're trying to figure out, you know, what kind of music people like, what makes people like that kind of music, why that music is good, what's different about that kind of music compared to other kinds of music, just stuff like that. Especially in businesses, I feel like you could apply this more in like, I don't know like a lot about businesses, but I feel like you could apply it in like whatever business you're trying to do compared to just like any other kind of math.
We love hearing from our students that it feels so obvious how applicable this math is to the rest of the world. And we're like, yeah, that feels obvious. That's our dream come true when we see students feeling like education, so applicable to almost anything you want to do in life. And that's really the dream of Course Kata. It's a curriculum that's based on theory, but we're not just satisfied with our initial students. We're constantly improving our materials based on research. And that's really a curriculum that started with theory, but improving based on data. And we call that the Better Book approach. And so I just want to show you a little bit of data that we have. A lot of times people feel like, wow, you're teaching both math and coding at the same time? That seems hard. And we're like, yeah, that's hard. But the reason that we use coding is that it helps students learn mathematical notation better because the coding feels more meaningful and does things in a way that eventually supports the learning of the algebraic notation. And so we've actually done some research to try and figure out what are the parts of programming that are difficult for students and how can we smooth that path. And one of the worst parts of programming is setting up the IDE or the coding environment, the place that you type in the code and press run. And so one of the things that we did was we integrated R with our course materials so that no teacher or student has to install anything. It's just right in their learning management system. They could just run the code, get the output right there, and it feels seamless. That way, students could focus on actually coding and not all the other stuff. And we've actually seen that doing this tremendously helps students feel less anxious about R. Their attitudes towards R improve from the beginning and end of the course. At the beginning of the course, students are pretty much in the middle how they feel about learning programming. Some students are anxious about it, some students not so much. But at the end of the course, most of our students report a positive experience, and even a lot of our students who started off being very apprehensive really become believers in coding by the end of the course. So integrating R into the course materials, that's not something a teacher could do by themselves, but when we work together with designers and developers, we're actually able to do things that teachers and researchers want, and designers and developers could actually help us achieve our dreams. We could also look at where our textbook falls short because there's a lot of places where we're not able to achieve the goal of all students learning hard things yet. So just to give you a small example, we have a place where we try to teach our students about the 5-number summary and what a quartile of data is. And we say in the book something like, it is important to note that what is equal about the 4 quartiles is the number of data points included in each. And we show this picture. Later on in that page, we ask students, the quartiles are equally sized. What is equal about the quartiles? And time after time, we would see only about 50% of students getting this question correct. And they would fall for these very interesting distractors, these distractors that implied that the quartiles had the same range or extent. And so what we did was we changed the picture that was on that page to specifically target that misconception. And we said the same text, but we changed the picture. And the question is, does this lead to an improvement? Well, in the Better Book model, we could actually check. We could look back at that embedded question and we could see, now we have almost 80% of students answering this question correctly and much less tendency, a much lower tendency to choose one of the distractors that's at the same interval. And so we're really excited about the possibility of improving course materials without journal articles, just based on things that teachers observe, the things that they've developed to help teach their own students. We're able to put that in the book right away so that all our teachers and all our students could benefit. And here's another example of how we use our data to improve the student experience. We could actually follow their learning behaviors over time. Learning hard things, it takes a longer time than 1 hour or 2 hours of learning. It takes maybe sometimes 10 weeks or 8 months, and we could actually follow student behavior over that kind of time scale. Here's one small example of research we've done to do this. We've looked at textbook interaction patterns that predict final course grades. And what we found is that there's 2 big cluster patterns of reading. One is kind of this, and these two clusters are actually predictive of final course grades. What you could see is that cluster 1 students show declining session length over time, and cluster 2 students, their session lengths are longer and more stable. And one of the things we find is that this kind of reading pattern or textbook homework completion pattern is associated with higher grades. And so then we could start to ask, why? Right? And those are the kinds of things that we could look at when we're actually able to look at student learning over a longer course. It's not just their behavior on one homework assignment, it's really their behavior that emerges over a longer time course. And so the mission of CourseKata.org is really to see flexible, generalizable, expert-like learning in all of our students. And we really think that we can't get there by ourselves. We can't get there just as researchers. We can't get there just as teachers. We can't get there just as designers and developers. We really have to all work together in order to see this vision. Thank you so much for your time. And I want to turn it over to questions now.
Great job, G.
That's so painful to make me watch that again.
So, G, I don't know if you were monitoring the chat, but you should take this first question about, does this curriculum at high school replace an algebra course, or is it utilized after students have taken an algebra course or attempted an algebra course? This is a great question.
Yeah, so it actually depends, because we have 4 different textbooks for high schools, and 3 of them are intended to be a kind of statistics or data science course after they've taken their core mathematics courses. And then there's one of them that's designed to be interspersed into an algebra course to help students kind of see immediately the applications of the algebra that they're learning. And so, and primarily the bulk of our current high schools, they're usually implementing this course as a standalone modern statistics or data science sort of course. So like a junior or senior year math course.
One thing that's true related to algebra is that most students who take algebra don't necessarily understand algebra at the end of the course. And so we don't rely on students to understand algebra in order to understand our statistics and data science materials. We sort of use coding in a way instead of using algebraic sort of derivations, because most students, that doesn't really help them very much. So for that reason, our materials can at least be tried by students who have a whole bunch of different experiences with algebra. So there are students who are taking our course because they failed Algebra 2, for example, and now they're taking our course. There are also students taking our course in 12th grade because they'd rather try data science than whatever else they were going to take as a 4th year math course.
And there are students who even take calculus who are just interested in just beefing up their real world data skills. And so we have a number of students who take that course just as a kind of elective math course.
Cynthia, you're asking about, does our high school supplemental text, and I think you're talking about the one we've designed to go with algebra maybe, provide a good foundation for project-based learning? And I think that our materials, and G can say more about this, but we have a real solution for project-based learning, which is this use of Jupyter Notebooks. Jupyter Notebooks are an authentic data analysis tool used by data scientists who work in industry and academics and public health and so on. And we've developed a project sort of template for doing projects in Jupyter Notebooks that result in really beautiful documents where you can run the code and see the analysis, and students can write their conclusions, et cetera. But we also feel like all of statistics and data science can't be presented in a coherent way just through projects. So we really try to balance, so the more structured presentation followed by projects. And that's really what our classes look like.
And I think just to follow up on that, I think there's kind of two uses of projects in a math class. One is like you learn the math and then you use projects to like apply the math, right? And the other is you use a project to help structure the different kinds of math that you'll learn, right? And we actually try to do both of those things in our materials. The textbook has kind of this one context that's kind of structuring all the math that they're learning. And that's kind of the project structures the math approach, right? And then in our in-class materials with our Jupyter notebooks, that's where students, they learn different things, and then now they're applying it to many, many new situations. And so that's one of the things our students say, and our teachers also say to us a lot, that they really appreciate seeing so many varieties of different data sets that they could apply their math to, because that's what really convinces them, wow, this is really applicable. You could almost think of anything and it could be, math could be applied to that context.
While we're waiting for any other questions, it's worth saying that we're always looking for teachers who want to pilot our materials, who are interested in figuring out the best way to embed them in the teaching that they're doing, whether they're teaching algebra or statistics or trying to teach data science. So please reach out to us if you're interested, and we can, we love to meet new teachers and get them started.
Yeah, you could go get an instructor account at coursekata.org.
Cynthia has signed up. Yeah, contact us, Cynthia. Love to work with you.
Yeah.
I feel like we're doing an infomercial.
I know.
One person signed up. All right.
Oh, it could be like those NPR, like, hey, like we just need 5 people to sign up by the next hour.
Right. Yeah. Our datathon.
Yeah.
Fundraising. Yeah. Oh, while we're waiting, Michael has a question. How are universities using the course Kata materials in an introduction to statistics course? And actually, Course Kata started out in universities, and currently I would say about half of our students taking Course Kata courses are in universities and about half are in high school, and both are expanding rather rapidly. Our materials have been used in all kinds of different courses and at all different levels of education. So in California, for example, we have our materials being used at the University of California, at the Cal State universities, and also in community colleges. Mostly they're used in introductory courses. Sometimes they're courses taught in the math department or the statistics department to fulfill a math requirement. But often we're finding that our courses are taught in the academic disciplines. So for example, statistics courses are taught in psychology, political science, sociology, public health, biology. All of these disciplines are offering sort of introductory level statistics courses, and we're being used in all of those. So if you're teaching at the college level or interested, we'd love to talk to you also. And also one of the things we're working actively at is on dual enrollment. Because our courses are taught at the higher ed level, we have the opportunity to get credit depending on the local situation and collaborations among higher ed and K-12 institutions to offer dual enrollment credit for students who can actually fulfill their high school math requirement or their college level math requirement before they get to college.
And I think we have another question that's relevant. Do you have an opinion on the current discussion about math pathways, data science as a replacement for third year of mathematics? Jim?
Go ahead, G.
Yeah, we talk about this a lot. And our kind of analysis of it is that, so just for anyone else who's not sure what this question is talking about, just to recap briefly, the idea is students take, typically the traditional pathway is Algebra 1, geometry, Algebra 2, pre-calc, and calculus, right? AP Calc. And so that's the traditional pathway. And some advocates in the state of California, Oregon, and others are saying perhaps for some students, we should have alternative pathway, all other pathways that are also equally rigorous and prepare students for college, but don't necessarily end up in calculus. For example, something like data science or a statistics pathway. And so that's the kind of rub. And I think the traditionalist side, I would summarize as saying, well, they say, yeah, algebra 2, we agree that it sucks for a lot of kids. And so we should improve algebra 2. We should improve algebra 1 and geometry and algebra 2. We should improve the traditional classes. And then others, and we agree with that. Yeah. And others are saying, well, maybe we should have other classes that are not just algebra 2. And we also agree with that too, right? And so, and the place that we think that both sides could actually agree on is that this algebra 2 really is a problem for many schools. And the not learning of algebra well is a problem for society writ large. And we think that's an important problem to work on. And we think data could have a part to play. And it could have two potential parts to play. One part is that data science and statistics could be a whole class. So it might be true that as a class, it might provide a solution. But I also think there's another part of the solution, that data could motivate the learning of algebra. And I think that's something that Course Kata really believes in, because, you know, we do a lot of advanced data teaching of it, thinking about it, doing of data science. And for us, we really think that a good understanding of algebraic functions is fundamental to doing data science. And so we would love to see algebra students really feeling like functions, they're great and awesome for modeling data. And so we really feel like that could really maybe bring some peace to some of the math wars, although maybe that's
I think our view is that anything that engages and re-engages students in mathematics and gets them excited about it is great for students. Anything that just kills their curiosity is not great for students. So there's various ways to approach that. You know, G, another question that came up from Jill is, how are you able to teach statistics without an algebra foundation? And I think this is a great question. A lot of it has to do with what statistics is about in the modern world. Statistics, you know, 50 years ago, before computers, used to be very tied up with algebra and deriving things like the central limit theorem, et cetera. But nowadays, statistics is more of a computational science. So although there's a great relationship to algebra, and especially things like the concept of functions, there are other things that are best represented through things like simulations, bootstrapping, randomization, things that people do now with computers to make progress on asking and answering statistical questions. So our view is that you can actually teach a modern statistics course with very little reliance on algebra. Although, like G said, we're finding that students get very interested in algebra. It depends on what you mean by algebra also. Functions are incredibly important because that's what we use to make statistical models. On the other hand, solving for X is not something that is very important for statistics, yet it's most of what students spend their time working on in algebra class. So algebra is important.
So some students might think, I'm not good at algebra because I'm not good at solving for X. But we would argue, well, you might still be good at algebra if you think of algebra as actually using functions, which is not necessarily always solving for X. That's kind of a small part of algebra. And there's so much more to algebra. And so we actually think, hey, there's hope yet for students who might not be great at algebraic manipulation to really be very interested and very good at the other parts of algebra. Well, I think we're nearing the end of our session. So if you have other questions, get them in now.
Or reach out to us. You can write to info@coursekata.org. And we're all there waiting to engage with you, answer your questions, and hopefully find ways to get going in different places, engaging students with math through data.
Thank you guys. Thank you for
Thank you,
coming.
everybody.